Hello everyone, I'm Yuze Zhang. So today I will talk about transport properties of non-reciprocal one-dimensional quantum channels at lens aluminum oxide and strontium oxide interface. So firstly, I would like to thank my group and especially my advisor Jeremy Levy and Patrick Irwin. So recently, quantum simulation has become more and more popular, and in the simulation, especially the one-dimensional electronic systems, have already shown many interesting and exotic phases of quantum matter. So in my group, we already write some electron waveguides and which already shows many remarkable properties such as tunable electron-electron interactions and the electron pairing without superconductivity. But in these systems, it is still lack of the strong spin-opt interactions. So here I describe a new class of the nanostructures. To begin with, I will firstly introduce the techniques we use in my group. In my group, you can use AFM, that is atomic force microscopic techniques, to write some nanowires which could combine into a nanostructure we want at the LAO-STO interface. By this, you can just write the main channel and some wires and the side gate by adding a positive voltage to the tip, and to write the barrier you can add the negative voltage. After finishing the device, I will cool down it into a low temperature, which usually about 20 millikelvin, and then you can see by the research there are some conductance and transconductance figures which shows the quantized conductance and rich subbands, and this is representative wave functions. So to reach those new nanostructures, I will did some new modulations on the AFM tip. For the lateral modulation, it is just achieved by tracing sinusoidal pace by the tip, and for the vertical modulation, it is achieved by changing the amplitude of the tip voltage. And when I combine them, it becomes a helical modulation, which is also a non-reciprocal nanostructure, so it could show some non-reciprocal property. So firstly, let's see the conductance and transconductance figures about the lateral and the vertical modulation. So in lateral modulation, you can see there is 1 square of each conductance plateaus that is similar, that is same as which is in the straight waveguide, but it shows new plateaus that is dropping while the magnetic field increased from 0 to 18 Tesla. So this is an interesting phenomenon. And in the vertical modulation, that my group has seen that some fractal electronic subbands has shown in the transconductance figures, which corresponding to some fluctuation in the conductance figures. That conductance has already been proved to correlate to the strong electron and electron interaction. Now let's see the comparing of the transconductance figures of these new nanostructures with the street waveguide. You can see that they all show some new subbands in the transconductance figures, and there are some fractured subband structures that is also different between them, and they exhibit their properties in a wider range of the magnetic field. So before talking about the non-reciprocal modulation, let's talk about a theory called the chiral-induced spin selective effect. This effect is talking about some electrons generating a magnetic field that is parallel to the direction of the motion, because they are moving in a non-reciprocal path, and this effect is attributed to the spin-optic coupling, and which could lead to the reduction of the elastic backscattering. So my group is interested about what could happen to our devices that is also a non-reciprocal structures. So now let's see the helical modulation that is strongly correlated to the theory. In the conductance figures, there are some overshooting. You can see here which is the plateaus before, but now it shows some oscillations, and the number of oscillation also increased when the magnetic field is increased. And in the transconductance figures, it shows some different fracture structures, and from the schematic figures you can see the effective magnetic field is in a different direction because it is combined with the magnetic field we add and the spin opto interaction magnetic field. And so for my future work, I will still focus on the non-reciprocal waveguide, but with some new structures. So now I would like to combine a sine wave and two inverted quarter arcs to form a unit and repeat it several times. Then it shoots a new non-reciprocal waveguide. The research will be done in the future. Yeah. So in summary, I just develop a nanoscale platform and then write some wires which combine into nanostructures, and then we do some research, see some quantized ballistic transport properties, and especially the engineering spin opto induction in the nanostructures. So this may be all of our future work. That's all.